Example 3. A manufacturer makes two products, X1 and X2. The first requires 5 hours for processing, 3 hours for assembling, and 4 hours for packing. The second requires 2 hours for processing, 12 for assembling, and 8 for packing. The plant has 40 hours available for processing, 60 for assembling, and 48 for packing. The profit margin for X1 is $7, $21 for X2. Express the data in equation and inequalities necessary to determine the output mix that will maximize profit. Now, let us focus on the circulation of this problem. Now, this company makes two products, X1 and X2. So here we are talking about two decision variables, X1 and X2. Now, to produce X1, we need 5 hours for processing, 3 hours for assembling, and 4 hours for packing. That means product X1 passes 3 phases: processing, assembling, and packing. Besides that, there is product X2. Obviously, to produce a certain quantity of X2, company or the production of X2 requires 2 hours for processing, 12 hours for assembling, and 8 hours for packing. It's just like X1. Of course, X2, like X1, passes 3 stages of production: processing, assembling, and packing. Now, let's check the situation in the plant. What available resources in this plant? No. Example states that plant has 40 hours available for processing. No. That means we need to produce, or we are restricted about the production of X1 and X2. So the quantity of X1 and X2 should not cost me more than 40 hours. Because the company has only 40 hours for processing, 60 hours for assembling, and 48 hours for packing. So the production of X1 and X2 should not precede 40 hours at the first stage, 60 hours at the second stage, and 48 hours at the last stage. Now, the profit margin for X1 is $7, $21 for X2. So $7 and $21 is the coefficient of X1 and X2. We mentioned before, $7 is instead of C1 and $21 it is instead of C2. C1 is the profit of 1 unit of X1 and C2 is the profit of 1 unit of X2. So it seems that our objective function is about maximization, and we can imagine that or predict the objective function like max z equals 7x1 plus 21x2. Now let's don't jump over the steps. Now example 3 requires to express the data in equation and equality necessary to determine the output mix that will maximize profit. Finished. Cut off. So the problem is about, the objective function is about how to maximize profit. Based on the data and information mentioned by example 3, we are going to construct the table. Now this table, the contents of this table are on the first upper row X1, X2 and resources. What do we mean by resources? In this case, the time available for the total process, the total time required for the total processing, 60, the total time required for assembling, and 84, the total time required for packing or available for packing. This is our restriction. Now the first column indicates the 3 process plus the profit. Okay, now let's move to the next table. Based on this table, let's move to the next slide, and we are going to design or to formulate the LPP or the linear programming problem to this example. Okay, referring to the table of LPP based on the previous table, so we selected the following aspects. Is based on the previous information. mentioned by example 3. First, LPP or linear programming problem involves two decision variables, x1 and x2, and the objective function is a profit maximization function. This is number 1. Let's move to the second aspect. There are 3 stages or 3 constraints: processing, assembling, and bagging. These 3 constraints or 3 phases or 3 stages, 3 machines, like that. The last component of LP is non-negativity condition is satisfied. Non-negativity condition is satisfied. Then max Z equal 3x1 plus 21x2. 7 is the profit of 1 unit of x1 as stated in the previous table. 21 is the price, or it is a profit of 1 unit of x2. This is our objective function. This is our objective function. Now let's move to our constraint. 3 constraints. 5x1 plus 2x2 less or equal 40. Less. Put in account all time, not all time of course, as stated by the law. The problem of maximization should be less or equal, while the problem of minimization should be more or equal resources. Now the constraint number 1 is 5x1 plus 2x2 less or equal 40. 40, this is time available for the stage of processing. The second constraint states that 3x1 plus 12x2 less or equal 60. Less or equal 60. 60 is the time available for the process of assembling. That means we cannot produce total quantity of x2 and x1 which cost me more than 60 hours. More than 60 hours. Equal or less 60 hours. For example, 10 units of x1, for example, just for example, 10 units of x1 plus 20 units of x2. So production of these quantities should cost me less than 60 hours or equal 60 hours, not more than. So let's move to the third constraint, the second restriction. It is about a backing. For x1, that means the production of X1 at the stage of packing should cost me 4 units or 4 hours. The production of X2 at the stage of packing should cost me 8 hours. 1 unit of X2. The total of X1 and X2 should not precede 48 hours. Should not precede 48 hours. Less or equal only. Now, the last is non-negativity condition, either to produce or not to produce. X1, X2 more or equal 0. More or equal 0. Example 4. An aluminium plant turns out 2 types of aluminium, X1 and X2. Type X1 takes 6 hours for melting, 3 hours for rolling, and 1 hour for cutting. Type X2 demands 2 hours for melting, 5 hours for rolling, and 4 hours for cutting. The plant has 36 hours for melting time available, 30 hours of rolling time available, and 20 hours of cutting time. The profit margin is $10 for X1 and $8 for X2. Reduce the data to equation and inequalities suitable for finding the profit, maximizing the output mix. Now, this company plans to produce 2 types of product, X1 and X2. The example mentioned 3 stages of production or 3 processes of production: melting, rolling, and cutting. That means each product should pass these 3 stages. Now, X1 takes 6 hours for melting and 3 hours for rolling and 1 hour for cutting, while X2 demands 2 hours for melting, 5 hours for rolling, and 4 hours for cutting. Now, let's check our available time for this plant or company. For melting process, the company has only 36 hours. For rolling process, the company has only 30 hours. And for cutting process, it has 20 hours. The profit of 1 unit of X1 is $10, while the profit of 1 unit of X2 is $8. Now, once we are talking about profit, Once the example 4 is talking about profit, that means the objective function is about profit maximization. That means the objective function is about profit maximization. 2, once there are 3 processes of production or 3 stages of production, respectively there are 3 constraints or 3 restrictions. For example, the first constraint illustrates or expresses melting. The second stage illustrates or expresses rolling, and the third constraint expresses the process of cutting. So, as we mentioned, let me repeat again. $10 is the coefficient of x1, indicates the profit of 1 unit of x1. $8 is the coefficient of x2, which indicates the profit of 1 unit of x2. Okay. Now, this table will help us to formulate the linear programming problem for this plan. Our goal is to maximize profit of this company using the mentioned data and equation. Reduce the data to equation and equalities suitable for finding the profit maximizing the output mix. Okay. Now let's convert this table into linear programming problem. Check the next slide. Now based on the previous table, we selected the following information. First, the problem contains 2 decision variables, x1 and x2. An objective function concerns with profit maximization. The second information is the process of production passes 3 stages: melting and rolling and cutting. Respectively, there are 3 constraints. Constraint for melting, constraint for rolling, and the last constraint is for cutting. Okay. The non-negativity condition is satisfied is satisfied. So the three components required for linear programming are satisfied. Now we are going to design the linear programming problem. Max z, this is an objective function. Max z equal 10x1 plus 8x2. Remember that 10 now it is a coefficient of x1 and 8 is a coefficient of x2. This coefficient is the profit of one unit of x1 and profit of one unit of x2 as shown in the previous table. The constraints should be three: one for melting, second for rolling, and the last for cutting. 6x1 plus 2x2 less or equal 36. This is about the process of melting. So, the quantity of x1 and quantity of x2 should be or should cost me less than 36 hours in the first stage. The second constraint is 3x1 plus 5x2 less or equal 30. This is about the process of rolling. So the total quantity of x1 and x2 at the second stage should not exceed 30 hours. The last constraint concerns with the last stage of production, which is cutting. x1 plus 4x2 less or equal 20. And finally we face the non-negativity condition where x1, x2 must be more or equal 0. Now this is our linear programming problem, which designed upon the collected information and data shown in the previous example. Example 5. The carpenter makes 3 types of cabinets: provincial x1, colonial x2, and modern x3. The provincial model requires 8 hours for fabricating, 5 hours for sanding, and 6 hours for staining. The colonial model demands 6 hours for fabricating, 4 hours for sanding, and 2 hours for staining. The modern one takes 5 hours for fabricating, 2 hours for sanding, and 4 hours for staining. The carpenter has 96 hours for fabricating, 44 hours for sanding, and 58 hours for staining. The expected profit margins are $38, $26, and $22 on X1, X2, X3 respectively. Express the data in mathematical form suitable for finding the optimal output mix. Okay. Now we have 3 decision variables, which are X1, X2, and X3. X1 stands for provincial, X2 stands for colonial, and X3 stands for modern. So the provincial model requires 8 hours for fabricating, 8 hours for fabricating, and 5 hours for sanding, and 6 hours for staining. Now, example tells us that there are 3 decisions variables and 3 phases of production: fabricating, sanding, and staining. Now, the available time for producing a certain quantity of X1, X2, and X3 at the first stage or the stage of fabrication is 96 hours. The total time for sanding is 44 hours, and the total time for staining is 59 hours. Example 5 gives $38 at the profit of 1 unit of provincial, $26 for colonial, and for modern is $22. That means the coefficient of X1 is 38, and the coefficient of X2 26, and the coefficient of X3 is 22. Now we need to express the data in mathematical form suitable for finding the optimal output mix. So once we are talking about the optimal output mix, that means a linear programming model. Of course, the problem is about profit maximization. Let us design table for example 5 in order to help us construct the linear programming problem. This table consists, of course, of 3 decision variables: X1, X2, X3, and the first column consists of three processes: fabricating, sanding, staining, and the profit. The last from the right hand, the last column from the right hand is about the time available for producing not for the time available for each process. For example, for fabricating, the plant has only 96. For sanding, the plant has only 44 hours, and for staining, the plant has only 58 hours. Now, according to these informations, we are going to formulate the linear programming problem for example 5. Referring to the previous table 1, the problem had three decision variables: x1, x2, and x3, and the objective function is about maximization. This problem absorbed from the previous information. This is our harvests. Respectively, the second aspect talks about the constraints. The production process involves three stages: fabricating, sanding, and staining. That means the LPB should contain three constraints. It is one constraint for fabricating, the other for sanding, and the last for staining. The non-negativity condition is satisfied. What that means? The quantity of x1, x2, and x3 must be more or equal 0. The non-negativity condition is satisfied. Then max x equal 38x1 plus 26x2 plus 22x3 as shown in the previous table. 38 is the profit of 1 unit of x1, 26 is the profit of 1 unit of x2, and 22 is the profit of 1 unit of x3. Also, they are known as coefficient of x1, x2, x3 respectively. Constraints. The first constraint belongs to the first stage, fabrication, where 8x1 plus 6x2 plus 5x3 must be less or equal 96. Unacceptable. More than 96 hours. The second constraint is for sanding, where 5x1 plus 4x2 plus 2x3 must be less or equal 44 hours. And the last constraint is dealing with the process of staining, where 6x1 plus 2x2 plus 4x3 must be less or equal 58. 96 is the available time for fabricating. 44 hours is available time for sanding, and 58 hours is available time for staining. The company have to produce or not to produce. Either not to produce. If not to produce, that means the production equals 0. If it plans to produce, that means it must be more than 0. So the non-negativity condition is x1, x2, x3 more or equal 0. This is about how to formulate the linear programming problem. Example 6. A game warden wants his animals to get a minimum of 36 milligrams of iodine, 48 milligrams of iron, and 16 mg of zinc each day. One feed wide one provides 3 mg of iodine, 6 mg of iron, and 1 mg of zinc. The second feed Y2 provides 2 mg of iodine, 6 mg of iron, and 4 mg of zinc. The first type of feeds cost $20, second cost $15 in terms of equation and inequalities. What is the least cost combination of feeds guaranteeing daily requirements?
Iodine. Zinc.
Okay. So now this man wants his animals to get a minimum 36 mg of iodine, 48 mg of iron, and 16 of zinc each day. Type. So now we face three constraints: iodine, iron, and zinc. Okay. Feed Y1 provides 3 mg of iodine, 6 mg of iron, and 1 mg of zinc. The second Y2 provides 2 mg of iodine, 6 mg of iron, and 4 mg of zinc. Type. The first type of feed costs $20. The second, $15. Type. Let us focus on the word costs. Cost. This example talks about cost. That means example concerns with cost minimization. Okay, and down, let's check the table. The table consists of two decision variables, y1 and y2. The available quantity of iodine is 36 mg, and the available quantity of iron is 84, and the available quantity of zinc is 16. Now Y1 requires 3 of iodine, 6 of iron, and 1 for zinc, while Y2 requires 2 iodine, 6 iron, and 4 zinc. The cost of 1 unit of Y1 is $20, while the cost of 1 unit of Y2 is $15. So this is the first time when we face a objective function for cost minimization. Now let us move to the next slide and to see how we are going to formulate an LPP for this problem. Let's see how to formulate the linear programming for the previous problem, or for the previous example 6. Now, focusing on the previous table, we will absorb the following aspects. Number 1, since there are two decision variables, y1 and y2, then the objective function consists of two variables and it deals with minimization. Once we are talking about cost, automatically the objective function is about cost minimization. Secondly, the objective function will be satisfied upon three constraints. What is that three constraints? Iodine and iron and zinc. Non-negativity condition is presented. Non-negativity condition is presented. Now, let's move to see how we are going to formulate the linear programming. So, as we mentioned, the objective function is about minimization. Then min z equal 20 y1 plus 15 y2. 20 is the cost of y1, feed y1, and 15 is the cost of y2. The guarantee of implement this objective function is to satisfy the following constraints. The first constraint is about iodine. 3y1 plus 2y2 more or equal 36. The constraints for the problem of minimization is more or equal B1, B2, B3. Right. The next constraint is for iron. 6y1 plus 6y2 more or equal 48. More or equal 48. We will try to produce a certain quantity of y1 and y2, y1 and y2 in order to minimize the cost. That's why the constraints more or equal. The third constraint is y1 plus 4y2 more or equal 16. More or equal 16. And the last is non-negativity condition. The quantity of y1 and y2 must be more or equal 0. Must be more or equal 0. Example 11. A food processor wishes to make a least cost package mixture consisting of 3 ingredients: y1, y2 and y3. The first provides 4 units of carbohydrates and 3 units of protein and costs 20 cents. The second provides 6 units of carbohydrates and 2 units of protein and costs 32 cents. The third provides 9 units of carbohydrates and 5 units of protein and costs 55 cents. Sorry. The package mix must have at least 60 units of carbohydrates and 45 units of protein. Express the information mathematically or express it in terms of linear programming problem. Checking dimension of formation. There are 3 decision variables: y1, y2 and y3. y1 as shown in this table requires 4 units of carbo and 3 units of protein. y2 takes 6 units of carbo and 2 units of protein, while y3 demands 9 units of carbo and 5 units of protein. The available quantity of carbo is 60 units and the available quantity of protein is 45 units. The cost of 1 unit of y1 is the 0.25 and the cost of 1 unit of y2 is the 0.32 and the cost of 1 unit of y3 is 0.55. So this example deals with the problem of minimization. So the objective function should take the shape of minimization, including 3 decision variables and 2 constraints. 3 decision variables and 2 constraints. Now let's see how we can formulate a linear programming problem according to the given information and data in this table. Let's move to the next slide to see. Reviewing table 7, we got the following aspects or statements. First, the objective function illustrates the type of minimization and contains two decision variables, y1 and y2. Two constraints should be more or equal to 0. That's correct. Two constraints, one for carbo and the next for protein. Now let's see the last formulation of the problem. Once example talks about cost, then the objective function should take the type of minimization. Minus z equal 0.25 y1 plus 0.32 y2 plus 0.55 y3, where 0.25 is the cost of 1 unit of y1 and 0.32 is the cost of 1 unit of y2 and 0.55 is the cost of 1 unit of y3. Subject to the first constraint stands for carbohydrates, and the second constraint concerned with protein. For y1 plus 6 y2 plus 9 y3 more or equal 60. Of course, there is some special cases where the constraints of minimization or maximization takes the shape of opposite shape. For example, for y1 plus 6 y2 plus 9 y3 may less or equal 60, less or equal 60, in order to make the constraint suitable for the problem of minimization. If the constraint is less or equal, then we are going to multiply inequalities by -1 to convert more or equal into less or equal. D'accord? And sometimes we get constraints equal to, just equal to, not equal, less or equal or more or equal, just equal to. In this case we have two options. Either more or equal or less or equal. In case of more or equal, that's good. In case of less or equal, we are going to multiply the inequalities by negative times -1. Okay. The second constraint is ty1 plus 2y2 plus 5y3 more or equal 45. That's good. The non-negativity condition is satisfied and presented. y1, y2, y3 more or equal 0. Let's move to new paragraph. It's about the standard form of LPP, linear programming problem. The standard form of linear programming problem is used to develop the general procedure for solving any LPP. The characteristics of the standard form are explained in the following steps. Step 1. All constraints should be converted into equations except non-negativity restrictions, which remain as inequalities. is condition number 1. How to make the constraints in standard form. How to convert the constraint to the standard form. So the first step is that all constraints should be converted into equation, except what? Non-negativity condition, which remain as inequalities and more or equal 0. Constraints with inequality type can be changed to equations by augmenting, adding, or subtracting the left side of each such constraint by non-negativity variable. These variables are called slack variables and added if the constraint is of less or equal type, and subtracted if the constraint is of more or equal type. Now, so standard form means addition or subtraction of a slack variable between brackets S. S stands for slack variable. So in case of type less or equal, in order to convert this inequality into equation, we need to add S. This is in case of less or equal. Less or equal means what? The constraint belongs to objective function of maximization. Now, if the constraint type more or equal, so between brackets about minimization, we need to add S. Okay. So add if the constraint less or equal, subtract if the constraint more or equal. This in case of type constraint, the subtracted variable represents the surplus of the left side. It is common to refer to it as surplus value variables. A surplus is nothing but a negative slack. To convert the following to standard form: 3x1 negative 4x2 more or equal 7, and x1 plus 3 plus 2x2 less than 3. Let's see. To convert these two inequalities, the first inequality, it will take the following shape: 3x1 negative 4x2 plus s1 equals 7 plus negative s2 negative s1 equal 7, and the next example or the next inequality, x1 plus 2x2 less or equal 3, and it will be in standard form: x1 plus 2x2 plus s2 equal 3 plus this x2 equal 3. This is how to convert inequalities into standard form. Okay, let us continue the debate about standard form. Step 2. The right side element of each constraint should be made non-negative. Non-negative. If required, is the standard constraint equation. For example, the inequation or inequalities 3x1 minus 4x2 minus 2 more or equal negative 2 can be written in the form of 3x1 negative 4x2 negative s1 equal negative 2 by introducing surplus value variable s1 more than 0, multiplying both sides times negative 1, we get negative 3x1 plus 4x2 plus s1 equal 2. Correct. Negative 1 and negative 1 multiplied by 3x1, negative 1 multiplied by negative 4x2, negative 1 multiplied by negative s1, and negative 1 multiplied by negative 2. Okay. Now, which is in standard form? The main here, the right side element of each constraint should be made non-negative. Non-negative. That's why we provided the process of multiplication by negative 1. Step 3. All variables must be non-negative values. A variable which is unrestricted in sign is equivalent to the difference between two non-negative variables. Thus, if n is unconstrained in sign, it can be replaced by x minus x2 or double comma, which is where x and x2 stars are both non-negative. So x apostrophe and negative x2 apostrophe are both non-negative. Step 4. The objective function should be maximization form or in maximization form. The minimization of function fx is equivalent to the maximization of the negative expression of this function fx, that is min fx equal negative max between brackets negative fx. Example 1. Express the following problem in the standard form, where max z equal 3x1 plus 2x2 subject to 2x1 plus x2 less or equal to 3x1 plus 4x2 more or equal to 1, x1 comma x2 more or equal 0. Introducing slack and surplus variables, the problem in the standard form can be expressed as max z equal 3x1 plus 2x2. Let's see how we can convert it, the two constraints in the standard into standard form. The first constraint is 2x1 plus x2 plus s1 equal to y plus s1, because the constraint is less or equal. The second constraint is 3x1 plus 4x2 negative s2 equal 12. Negative s2 because the constraint is more or equal. S2 indicates the second constraint, S1 indicates the first constraint. Now, the non-negativity condition can be expressed as x1, x2, s1, s2 more or equal 0. Example 2. Reformulate the problem into the standard form. Given min z equal to x1 plus 3x2, subject to 2x1 negative 3x2 negative x3 equal negative 4. It's a different. 3x1 plus 4x2 negative x4 equal negative 6, and 2x1 plus 5x2 plus x5 equal 10. The last constraint is 4x1 negative 3x2 plus x6 equal 18. Solution. Here x3, x1, x4, x5 and x6 which are all non-negative are the select variables. The decision variables are unrestricted inside. Putting x1 equal y1 minus y2, x2 equal y3 minus y4, y5 x5 equal y5, x4 equal y6, x5 equal y7, x6 equal y8 instead. Now min z equal 2x1, x1 equal, we mentioned x1 equal y1 minus y2, then x1 equal 2y1 minus 2y2 plus 3x2, x2 equal y3 minus y4 plus y3 plus 3y3 minus 3y4. Now we can take it out of the brackets, and it can be 2 open out of 2 inside brackets y1 minus y2 plus 3 open the bracket y3 minus y4. The mean here is, instead of x1 we will insert, instead of x1 we will insert y1 negative y2, and instead of x2 we will insert y3 minus y4. Then 2x1 negative 3x2 negative x3 equal negative 4. x1 as mentioned equal y1 minus y2. Then it will be it will be negative 2y1 plus 2y2 plus 3y3 negative 3y1 plus y5 and equal 4. Just follow the givens, putting x1 equal y1 minus y2, x2 equal y3 negative y4, x5 equal y5, x4 equal y6, x5 equal y7, and x6 equal y8. So we are going to compensate, to substitute, just to substitute, and we will get the whole constraints. The non-negativity condition, it will be y1, y2, y3, y4, y5, y6, y7, y8 more or equal 0. More or equal 0. The main mission is to substitute x1 by y1 negative y2, x2 by y3 negative y4, x5 by y5, x4 by y6, x5 by y7, and x6 by y8.